Hi students, and welcome to Preliminary Chemistry and the Chemical Earth video series. In this particular video, we're going to have a quick look at atomic structure. Now, I hope most of your understanding of the model of the atom has come from previous studies in years 9 or 10, and so most of this should not come as a big surprise to you, but let's just review a few things anyway. The current model atom that we use to explain the behavior of atoms in chemical reactions is the Niels-Bohr model. In this model, we have protons and neutrons located in the nucleus. Protons have a positive charge, neutrons have zero charge, they are neutral, and they are located in the very center of the atom. That's where all of the mass is. So this represents the mass of the atom. Now, electrons do have mass, but they have only a very small amount of mass, and they do not significantly contribute to the mass of the atom. Nevertheless, we find that they are distributed around the outside of the nucleus. The electrons are around the outside in energy levels, sometimes called shells or orbits, and these have particular characteristics. We do note, for example, that there are only two electrons in the first energy shell, the n equals 1 shell, 8 electrons in the next one, and so on. Now, some of the rules that we've looked at, you've probably gone to as far as, say, number 20, which is calcium, which has an arrangement of 2, 8, 8, 2. That all works really good until we get to the transition metals, and then some rules start to get broken. So we won't worry too much about them just for the moment, but we'll just make sure that we understand that there is a maximum number of electrons in each of these different energy levels, and the outer shell, the one that's most important, is the outer shell. This is often referred to as the valence shell. And this is because this is the one that tells us how the atom is going to behave in terms of whether it gains or loses electrons, or is prepared to be involved in sharing electrons with other atoms. Within each of these shells is a number of subshells, and that is what allows us to look at how the shells will fill, how each of these electrons will populate the atom, and where they will be distributed around the nucleus. There are a number of important consequences of the understanding of shells and subshells. A certain amount of energy, a quanta of energy, can be introduced to an electron in order to move it from one shell to another. This is also sometimes called a photon, a sort of little measure of electromagnetic radiation which can drive the electron from one shell to another. When it returns from that shell to its original shell, it will release that energy. And we see this in flame testing, we see this with fireworks and things like that, where the electrons are excited, they move from one shell to another, and then they return back to their ground state. Now, if the amount of energy that's being put in is sufficient, then the electron can escape altogether. If the electron actually escapes from the influence of the nucleus, then we have an ion. In this case, if it's lost an electron, it is a positive ion, which is also called a cation, not a cation, but a cation. And we'll look at these in a little bit more detail when we look at ionic compounds in the next video. There are a number of symbols that we use to identify each of the atoms, because there are three important things that we need to be aware of whenever we're looking at atoms. The first is the symbol. So this is the symbol for the element. So that may be H for hydrogen and C for carbon. Then there's a number, the atomic number. The symbol Z is used to represent the atomic number, and this represents the number of protons. Only the protons define the atom. The electrons can be gained or lost, and neutrons can change in number as well, and that gives rise to different forms of an element called isotopes. But the protons actually define it. So if there is one proton, it must be hydrogen. If there are 6 protons, it must be carbon. And then the other number is the mass number. And the mass number indicates the total mass, which is equivalent to the number of protons plus neutrons. We don't assume that the electrons are going to contribute to the mass when we work this out. So if hydrogen has 1 proton already but no neutrons in its nucleus, then it has a mass of 1. Carbon, on the other hand, if it has 6 protons and 6 neutrons, will have a mass of 12. We can have carbon with 6 protons and 7 neutrons. We can even have a carbon with 6 protons and 8 neutrons. These, unfortunately, are unstable, and so they will decay radioactively, and that's something that we'll look at in future parts of this course. So what I'd like you to do perhaps is stop the tape, go through, stop this video and go through and see if you can identify from the periodic table all of the different types of numbers of protons, neutrons and electrons that are present in the most common of the isotopes of each of these elements. I've already done 2 of these for you. So hydrogen is 1, so it has 1 proton, it has 0 neutrons, it has 1 electron, and when it loses that electron, it can form an H+ ion. Carbon is a little more unusual. It has 6 protons and 6 neutrons. It also has 6 electrons. It can form a carbide ion, a 4-, but it's most often involved in covalent bonding. I'm going to put that just underneath it, covalent. The rest of them I'll leave for you to go through and ask me in class if you've got any questions. Thanks for watching.